I want to go back a few slides and review this topic real quick. So going back to the magnetic quantum number, remember the magnetic was the orbitals and how many orbitals each block holds. So the S has 1, the P has 3, and remember how we talked about it's on different axes. So you have, in here you have something on the X axis, something on the Y, and then this one was on the Z. So remember, it can be just like we wrote here. Anytime you're on an orbital for the P, there was always going to be 3 of them, and if it was D, it was always going to be 5. Okay, so it can be on different axes whenever you're talking about this. This is something we've kind of already talked about. Again, the sphere, the dumbbell, the D was a double, and make sure you know that it has 5 shapes. This is something you really need to put a star beside. We're talking about the period, and really remember, N is the principal, which means the energy level. That's the key to this, is you must know this terminology, that it's the energy level. That's where you will struggle if you don't know the terminology. When we're talking about when N equals 1, I want you to see something real quick. When N equals 1, there are 2 electrons. And what I mean by that, when you are looking at when N equals 1, it is the first 2. There are 2 things in that row. So that means there are 2 elements, which means there are 2 total electrons whenever you count it up. Going back, if you will notice, when N equals 2, there are 8 total electrons. Well, where did that number come from? Follow the blue. There are 2, which count in the S, and then there are these 6, which account for the P. Then, if you go back one more time, the purple, when N equals 3, there are a total of 18. Where did that come from? You've got the 2 in the S, you've got the 6 in the P. Well, where in the world did those other ones come from? Okay, well remember, what did we have to do to the D block? We had to raise the D block up. So 10 more come from right here. So as you can imagine, last one, when N equals 4, it is all of them, the S, the P, the D, and the F. So we have 4, this is also 4, this is also 4, and then finally you also have to include the F block. Now, I know that you're not required to know the F block, but just make sure that you account for it whenever you're counting electrons. So that is what all of this means. S equals 1 orbital because 1 orbital can hold 2 electrons. That's what I mean. Remember, every orbital can hold a total of 2 electrons. Well, since P has 6 total electrons, it's going to need 3 electrons. So whenever we did the orbital diagram with the arrows, remember, if this was number P, whatever number that was, we always could put 6 total electrons in this thing. Just as we had D has 5 orbitals, 1, 2, 5. And we could put 10 in there. And F, we never did one of these, but if we had to, we could. And it would have 7, which is exactly what it would look like. And if you did 2 arrows per line, that would be 14 total electrons, and that's how many total elements are in that block. The 3 principles that we had to adhere to. Aufbau, remember, you fill orbitals lowest to highest. Energy levels, remember, I kind of referred to this as kind of the roller coaster idea. And the way you can recognize it if something is skipped, really. So when you start with 1S, if you're going all the way through, if an energy level is skipped, then you can account back to it for Aufbau. Pauli, you cannot have the same 4 quantum numbers. Now remember, I never really started assigning quantum numbers. The only thing that I did was tell you that it was kind of the address. I just want you to remember what Pauli's exclusive principle is, because you're going to see it. Hund's, there's a big definition to it. I didn't really necessarily write it out. If you want to know the true definition, look it up in your notes. It talks about how equal energy levels must be separated, and if they're within the same energy level, they must be spinning the same way before you put an electron beside it. So really, again, it's kind of like having 3 rooms in a house. You want to fill all the rooms up before you put 2 people in the same room. So to space the electrons out in different orbitals, if there is room And remember, once there is any more room, you can double them up. But once you double them up, they have to be spinning opposite. One has to be spinning up, one must be spinning down. That is the biggest difference. Now, the next little part that we're going to get into, I'm going to be writing the whole time, and that is orbital notation. And I think there are 2 of these on the test right now. Remember, the big key here is you're going to have to know what to do, because I'm not going to tell you. Orbital notation is using the arrows. And so I'm just going to kind of throw an example up here. I'm just going to do oxygen just to kind of show you. So now, again, if you'll just follow along the periodic table, if you'll follow along the electron configuration, how to fill it, we always know we start with 1s first. And so we're going to go up 1, and there's another place to put it. So we're going to go down. Well, and let me go back and say this. That oxygen has 8 electrons, so we're going to need 8 arrows here. After 1s, we have 2s, so it's going to be ending there. And then after 2s, we have the p, and there's always 3 orbitals in the p. So we have, excuse me, this is 2p. So we have 4 left. So we can go up, 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 and now they're full. Remember, always space them out, fill them up, and then come back and put down. So that is 2, 4, 6, 8, and that is the last thing you will have to write. Now I'm going to go ahead and go back and kind of talk 1 second about something, and that is total number of orbitals per energy level. Alright, so this is going to kind of take a second to draw this out. Alright, so what I want to write here is the N, which again is the principal, or really it's the energy level. That says energy level, okay? When N equals 1, the only block you're going to have is S. So what that tells me is that S is going to have 1 when N equals 1, there's just an S, so there's 1 orbital, so total number of orbitals in the first period is that. When N equals 2, we have an S and a P. Now, if you'll note, we've already kind of covered this. If you'll look at the very, very first worksheet we did on this, we covered this in a chart form. This chart is kind of what I'm recreating. So the S always has 1 orbital, and the P always has 3 for a total of 4. Now let me show you on the periodic table what I mean. When N equals 2, again I'm going to draw it with the blue line. So we're talking about here, we're talking about here. So this is 1, this is 1. So this is only 1 orbital in the S, and there are 3 orbitals in the P. And that 1 plus 3 is 4, is what I mean by that. Okay, when you have the third energy level, you have the S, the P, and the D. So the S will have 1 orbital, the P will have 3, and the D has 5. So the total number, and again, the key word here is orbitals, will be 9. And then finally, 4, you have all of them, S, P, D, and F. So same thing again, S is 1, P is 3, D is 5, F equals 14. Excuse me, not 14, let me change that. That is 7, not 14. There's 14 total electrons, but there are 7 orbitals. Okay, so 10, so 16 total. Okay, so 16 total orbitals. So you really, really, really need to focus on this. So I'm going to go back to this. So again, that is the, let's go back to orbital notation, which is using your arrows. Let me do one more example just to kind of show you. let me do CR. Now this is going to be kind of a longer one. CR has 24 electrons. Now, and if you'll do this, it'll make your life so much easier. If you'll notice, CR, its final value is going to be 3d4. That's going to be the final value of it. So that's where we got to get to. All right, so the first one is 1s. Then after that is 2s. The next one is 2p. I'm going to go ahead and finish this out. 3s, 3p, 4s, 1, 2, 3, 4, 5, and this is 3d. Okay, so I'm going to go in and backfill. Up, 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 down, 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 up, down, up, 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 down, 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 up, down. All right, now, so we're in the 3D. And again, if you will notice, I wrote it over here. The final value needs to be 3d4, so I need 4 more arrows. So it's going to be up, 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 up. And it's going to leave this last one empty. There's nothing is going to be there. So that is going to be your final answer. So again, that is orbital notation, and orbital notation uses arrows. All right, 2 more slides. Electron configuration. Now, electron configuration, this one uses superscripts. Okay, so what I'm going to do is I'm just going to go back and I'm going to show you this. I just want to rewrite it for this one because it's going to make life easier. So oxygen. So what we're going to do is we're going to take these arrows and we're going to turn them into superscripts. So hopefully this is easy for you. But it's going to be 1s, 2, 2s, 2, and then we have 2p, 1, 2, 3, 4. So it's going to be 2p4. And then the electron configuration for chromium, the longhand version, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then finally we have 3d. Now it's not full, so we have 1, 2, 3, and 4. So it'll be 3d4, and that is the electron configuration for that one. I'm going to do another one just to kind of show you. So let's look and let's just pick a random one. Just to make it nice and simple, let's just do sulfur. Okay, we're going to do this. So let's go ahead and label this and figure out what this is. We know that helium, even though helium moves here, we know that this is going to be period 1, period 2, period 3. We know, so it's period 3. We know this whole entire block is the P block, and this is 1, this is 2, this is 3. So it's going to, its final value is 3p4. So that's where we have to stop. We have to start in the very beginning. So let's go ahead and kind of work this in. So we know that we have right here 1s2. This is 2s2. Here, this is 2. Let me rewrite this. I got ahead of myself. 2p6. Here, 3s2, and then finally, we already know what our last value is going to be, and it's going to be 3p4, and that is the electron configuration for sulfur. Now, just to kind of make a point of emphasis, the very last one we're going to stop at is right here. This is the last value that you're going to be responsible for, and that value is 6s2. So everything from here after is out. None of this you will be tested on. Every bit of that is gone. So the BA is the last value that you will be required to know. Because, and the reason why we're stopping at 6s2 is because after 6s2 is 4f. Okay, 4f. So that's why we're going to stop there. All right, last slide, and that is the noble gas. configuration. And some of you are having trouble. Yes, I know I misspelled that. Noble gas configuration. So let's go back to the periodic table and let's figure out how to do it. So what if I wanted to do strontium? SR. This is the one I want to do. Strontium is number 38. So what I'm going to do is I'm going to go to the noble gas that is prior to it. So if it helps to draw a line, and krypton is number 36. That is the one prior to it. So what we're going to do is, remember, we use brackets. So put KR in brackets. And then after number 36 is number 37. Well, what